So we are live now. Artide, do you want to introduce him?
Sure. Okay. It's a real great pleasure to have Professor Shachar Lovett from UC San Diego. Shachar has done extensive work, is very broad in the field of mainly combinatorics and theoretical computer science. And without further ado, I'll just let Shachar take it away.
Thank you, Arkadir. Hi, everybody. So what I want to tell you about is some work that this area I've been working on for the last year or so, and I'm very excited about it. And it sort of all started, and I'll tell you later, from this work of Zander Kelly and Raghu Meka about a year and a half ago, where they developed new techniques to prove significantly better bound for some problems in additive combinatorics. And all of this is sort of based on trying to understand what they did and see how these ideas can be applied to other settings, to more combinatorial problems, to algorithmic problems, and so on. So I'll tell you about some work that we have, and we have more things in the pipeline. But I think some of you might get also excited and sort of jump on this bandwagon and see why these techniques are really exciting. Okay, so this is what I'll tell you about today is joint work with several people. So Amir Aboud, who's at Weizmann, Nick Fisher, who was at Weizmann at the time, I'm not 100% sure what his affiliation is today, Michael Jeber, who's a PhD student at Austin, Zander Kelly, who's now a postdoc at IIS, Raghu Meka at UCLA, and Anthony Astuni, who's a PhD student at UCSD. So basically what I want to tell you about is mostly these notions of regularity that come up in mathematics, and also we have our own notion of regularity that is useful for us. A little bit about the proof ideas and mostly about some applications, and we'll see how much time we have. I'll tell you about some applications that we have, and then some future ideas. And please, if you have any questions, stop me, ask. The goal is that everybody should understand everything. So what is regularity in general? Like what's a high-level idea? What's happened? My PowerPoint got stuck. Okay. So what is regularity? So let's think about graphs. So that's maybe the most common issue of regularity. Many people, heard about, the Szemeredi regularity lemmas, which is like a very powerful tool in graph theory. So regularity says that if I give you a graph, you can break it into a small number of parts that essentially look random. It doesn't matter if your starting graph is like, adversarial, pathological, doesn't matter. You can always break it up into a small number of parts that sort of look random, and looking random turns out to be extremely useful for many, many applications, both in mathematics and in TCS and algorithms. And what I want to tell you about are three notions of regularity. So the original notion that Szemeredi developed in the middle of the 70s, and his main goals were toward proving results in additive combinatorics, in particular what's known today as Szemeredi theorem. And then there was a sort of a refinement or a variant proof by Frieze and Kannan about 20 years later, because as you will see, while Szemeredi's regularity lemma is a very powerful tool, qualitatively, the quantitative bounds that it gives are very, very poor. And so it's for many quantitative questions, it's essentially useless. And the whole point was to try to get something that is more effective. And I'll tell you about the new notion of regularity that we developed that is even more effective than the Frieze-Kannan one. So I'll tell you about the parameters and so on as they come up, in the discussion, but really it's all about trying to find notions of regularity that give you better quantitative control over the parameter that you care about. Okay, and I'll tell you a bit about applications later. Again, for now, ignore the details. It's mostly going to be an application in communication complexity. And then if we have some time, some applications for matrix multiplication algorithms and combinatorics. But we'll see how much time we have. Maybe I won't get through all the applications. So while I was telling about graphs, actually it's much cleaner to present everything I'm telling you about today in the language of matrices. So from now on, just think about Boolean matrices, which if you want, they can be thought about the adjacency matrix of a graph, or you don't have to, just a Boolean matrix. And here are the notations I'm going to use. So I'll think of A as a matrix, so A of X and Y is just a XY entry of the matrix A, so row X, column Y. So it's a 0, 1, number between 0, 1. I'll denote the size of the matrix. Like that. By the way, can you see my cursor?
Yes.
Okay. This is how I denote the size, like the number of entries of A. And the other parameter that's going to impose is the density of a matrix, the fraction of 1. It's a 0, 1 matrix. The fraction of 1 is just going to be the density of A, expectation of A. So in general, I'll think about the matrix as a function that takes a row X and a column Y and outputs 0 and 1. And that's just going to be its expectation. So the density of the ones. So there's one more notion that's useful here, which is that of a rectangle. So a rectangle is just a submatrix. So it's a subset of rows times the subset of columns. So when I draw it contiguously, but it doesn't have to be contiguous. So the rows is just some arbitrary subset of rows X, and the column is just some arbitrary subset of columns Y. That's a rectangle. And then the last important notation I will need is the expectation of a matrix on a rectangle, which is just what you expect to be. So you just restrict this rectangle and you ask, what's the fraction of ones on this rectangle? So these are all the notations I'm going to use. That's it. So I want to make sure that everything is clear. Is there anything in this notation that is unclear that you want me to explain?
Size is number of rows, number of columns.
Sorry, what?
Size is just the number of entries.
Size number of entries. If it's like an n by n, it's n squared. Yeah.
Is the matrix A random because you're taking an expectation?
No. A is an arbitrary 0, 1 matrix.
So what does it mean by expectation here?
Oh, it just means density. The expectation of the row and column.
All right.
Sorry, this is maybe, I don't know, maybe that's not a good notation, but I just think of that as a density. If I think of A as a function of the row and the column, then its expectation of the rows and columns is just a density of it. It's a fraction of ones in it.
Got it. Thank you.
Good. Good. Any more questions? Yeah, nothing here is random. The matrix is some arbitrary matrix somebody gave you. Could be from, you want to study some combinatorial problem. Could be because you want to study some algorithmic problem, some arbitrary metrics. Okay. So what is regularity? So let me start by Szemeredi regularity. How does Szemeredi define regularity? So let's first do it sort of by picture. So a matrix is regular if you take a smaller submatrix, but not too small, and you ask what's the density here, it looks the same for all submatrices. Like for example, see this picture on the left, it has about, the average is about maybe 50%, right? It has white, let's say white is 1, black is 0, grays, the average here is about 50%. And it doesn't matter how I move this red rectangle around, it's going to stay 50%. And while the matrix on the right is not regular, right? If I put the red square at the top, at the bottom right, it's like very white. Let's say close to 1. If I'm going to move it here, it's going to be close to 0, right? So the matrix on the right is not regular. As I move the rectangle, the averages change. The matrix on the left is regular. It doesn't matter how I place this red rectangle, it's going to average be close to 50%. Okay? So this is sort of a regularity by picture. Let's define it a bit more mathematically. So we said the matrix is epsilon regular. So I use one parameter, epsilon. If you take any rectangle of size at least epsilon, this is the matrix, the average over this rectangle is the global average plus minus epsilon. So I'm using epsilon for both parameters. You could have used two different parameters. Doesn't make a big difference. I want to simplify things. So I use one parameter epsilon for our approximation, both for how small this rectangle can be, so I can actually guarantee something here. Of course, if this rectangle is super tiny, I can't guarantee anything. Just looking at a single pixel in a picture. But as long as this is big enough, it's supposed to average things out. So this is at least epsilon fraction of the entries. The average here should be the global average plus minus epsilon. Okay, so this is how Szemeredi defined regularity. It's a very strong notion. For every rectangle, it should be true. Every small rectangle. Okay, but then, of course, if somebody is giving you an arbitrary matrix, very likely it's not regular.
Excuse me.
Something else.
Does
Yes.
this have a connection to the regularity based on every vertex having the same degree or not?
I'm sorry, I didn't understand you.
There is a notion of regularity that just says that all vertices have the same degree, a regular graph.
This is true. That's another notion of regularity, which is not related.
It's
to what I'm
not.
talking about. Yeah, regular is an overloaded word. It means many different things. In this notion, it does not mean anything about the degree.
No. I think the confusion, Shachar, is that Szemeredi's regularity lemma is defined with respect to usually graphs. And
I know it's defined with respect to graph, and here I'm slightly changing it to be defined with respect to matrices. And you can think, if you want, about the matrix as a adjacency matrix of a bipartite graph. I mean, if you like it, I prefer to think about it as a matrix.
Sure.
I agree. Graph would be basically a symmetric matrix. That's another way of thinking about it.
Yeah.
But basically, one way to think about regularity is that if you look at this matrix and you on a sub part of it, but you don't look too closely, and you average things out, it looks about the same everywhere. It's not like they're like, hot, like, if you look about terrain, the terrain is overall mostly flat. They're not like hills or valleys or anything like that. No big areas like too high or too low. Okay, but if a matrix A is not regular, it's an arbitrary matrix, how can you relate to regularity? So here is what the famous regularity lemma comes into play. And it says, take any matrix whatsoever, arbitrary. You can always partition it into a small number of rectangles, like here, such that not all, but almost all of them are going to be regular. Like maybe here in this picture, I took this matrix and I broke it up into these parts. And you see this one here is maybe not regular, but all the rest are regular. Now, they might not have the same density. Maybe this is more leaning towards white, and this might be more leaning towards, gray, and this is maybe more leaning towards black, but each one individually is regular. And formally, it says that for every epsilon, any matrix A of any size whatsoever can be partitioned to some number k of epsilon parts, that most are epsilon regular. Most can be 99%, 1 minus epsilon, doesn't really matter now. And this turned out to be an extremely useful theorem because it allows you to analyze, if a fixed epsilon, let's say 1%, there's some value of k that is just an absolute constant, depending on 1%, such that any graph, as large as you want, can be partitioned to k parts, and most of them are regular. And this is extremely useful, has tons of applications in graph theory, also in algorithms. And
When you say most, it is by the number of parts or the weight of the parts?
1 second. Sorry, 1 second. So assume all the parts have about the same size. Okay,
Right.
so the parts are the same size, or about the same size. The bottom part, ignore it, just a side comment.
And can you take the rectangles to be linear, contiguous subsets of rows and columns in this?
No, you can't do that because there is no notion of order to the rows and the columns. So all these notions of regularity that we have here are invariant to permuting the rows and the columns. So there is no inherent notion of order here to the rows and the columns.
It's arbitrary linear ordering. Would there be a special partition that
What you're asking that if somebody gives you an order, can you hope to get a partition with the same order?
Yeah.
Maybe, but this is a different notion.
Okay.
I don't know the answer, but it's a very good question, but not related to what we're trying to do, because here all these notions that we're trying to study here are invariant to reordering. It's like a graph. I will give you a big graph and ask you some question about this graph. Like, does it contain a clique or something? The way you choose to label the nodes doesn't really matter.
Thank you.
Yeah. But again, there could be other notions of regularity, and there could be many of them. So here we can one of them. So this is a theorem that somebody proved, and really the main caveat of the theorem. Sorry, I don't know why my PowerPoint is like not acting. So this has like many applications, starting from Szemeredi theorem on arithmetic progressions and many applications afterwards that people have found. But the huge caveat here is this number k as a function of epsilon is huge. It's a tower. It's a tower of height, something like 1 over epsilon squared. And actually, it's known that this is necessary. It's not just an artifact of the proof. So Gauss proved in the 90s that really, to get this very strong notion of regularity, you need K to be tau. So to some extent, if you're hoping to use this regularity lemma and you hope to get any type of meaningful quantitative bounds, you're out of luck. It's not the right tool. It's a very good tool to get qualitative bounds, but not strong quantitative bounds. And so people have asked, can we find maybe slightly weaker notions of regularity that are still useful for applications, but maybe that give better quantitative bounds? And this is what Frieze and Kannan did about 20 years later. They defined a different notion of regularity, I'll explain to you in a second, that gives you less guarantees, still useful for some applications, but the main benefit is that you don't need to pay this huge tower parameters, you get better parameters. We'll see what. So what is this Frieze-Kannan regularity? So it actually starts with the following setup. Let's say somebody already gave you a matrix already with a partition. So you don't need to find a partition. Somebody gave you a matrix with a partition, 2 parts, 2 rectangles. Maybe some are regular, some are not regular, I don't know. And think about the following process. In each rectangle, average that completely. So it's like you look from very far apart and you average all the values inside the rectangle, just one specific value. So for example, if this represents a graph and I partition this graph to like 10 parts, so now for each part, I just remember the average number of, let's say, edges in this part. And I ignore everything else. Just have one number for each rectangle in this partition. And Frieze and Kannan said that this partition is regular if I take a large rectangle, in this case, this red rectangle, and it cannot distinguish this very fine picture on the top with all the details, and this very coarse picture on the bottom that has only sort of, average, global averages inside every smaller rectangle. And they said if this happens, we say that this partitioning is weakly regular. So it's a slightly more refined notion of regularity, but it's a definition. And again, you can make this more precise. Let's ignore this quantitative bounds for now. And the main benefit of their regularity lemma is that they could get the number of parts that you need not to be some tower, crazy tower of 1 over epsilon, but only be exponential. So much, much better than what we had before. And also they showed that while the guarantees are weaker, they are still sufficient for many applications. Not all applications of regularity lemma, but for some applications. And this led to improved quantitative bounds for some problems in combinatorics and in algorithms.
Sorry, Shachar, I got confused about one thing. So
Yes.
you said that you are now given an arbitrary partition, right? So what do you mean that it can be where is the K coming from?
So really what it means is the following. What's a CRM? It said, take any matrix whatsoever. You can partition it to K parts such that each part by itself locally is maybe not be regular, but if you look at them from far enough away, then they look regular. And particularly every rectangle of density epsilon cannot distinguish your original matrix from this sort of average matrix.
What does it mean to not be able to distinguish?
So it means that the average over this rectangle over the original matrix,
Yeah.
the average over this sort of average matrix are the same up to plus minus epsilon.
Okay.
Now, of course, if this red rectangle respected the partition, the average would have been the same. But it doesn't have to. It will go cross tiles in the middle and so on. And the guarantee that you can always find such a partition. Okay. So it's a weaker notion, but it's still useful for some applications. And it gives exponential bounds. And really, what the thing that we've been trying to do is to ask for various questions in combinatorics, in other areas. It seems that exponential is not the right answer. It's too much. We want to get polynomial, maybe quasi-polynomial bounds here, but not exponential bounds. And we were trying to understand what notions of regularity could still be useful, but give you polynomial or quasi-polynomial bounds here, instead of exponential bounds. Because for some problems, that seems to be the right answer.
Shachar,
Yes.
So for the Frieze-Kannan regularity, is exponential 1 over epsilon squared required?
Yes,
I see. Okay.
it's required. Yeah, in both cases, it's required. Yeah. So, all good. So really, if you think about Szemeredi versus Frieze-Kannan, the Szemeredi regularity notion is stronger guarantees, but you pay the price that you pay much worse quantitative bounds. Frieze-Kannan give you much better quantitative bounds, but still they seem to be lossy for many applications. Seems like exponential is too much. There should be something better that you can do. Okay, so now I'll tell you about our new notion. So our new notion, we're going to define it in a way that if you don't have this property, it would naturally tell you that it should be clear what you should be doing. And you'll see what I mean in a second. There'll be some obvious way of fixing a violation. And the main benefit of it will be that now we can guarantee that the number of parts in our whatever regularity that we're going to have is only quasi-polynomial and not exponential. And the weaker guarantee is going to be that it's going to be look even less random than all the other things, but there's going to be a new twist. The new twist is going to be that of mixing, which is if you take two matrices, let's say, that are spread regular, our new notion of regularity, each one individually might look very much not random. But if you multiply them, now they become very much close to random, very close to uniform. So while in previous notions, single elements looked random, now we're going to get that single elements don't look random, but when you mix two elements, in this case, multiply two matrices, they look very close to random. So this will be the new twist. And this tends to also be useful for some applications. And again, the main benefit of all of that is that our goal is to get good effective bounds, and for this we need to control the number of parts in the partition, and now we can get quasi-polynomial bounds instead of like exponential or tau type bounds. So let me tell you what is this spread regularity. It's going to be relatively easy to define. So I give you a matrix A. We're going to have two parameters, D and epsilon. And very soon we're going to fix epsilon to just be an absolute constant of 1%. So really we're only going to have one parameter, D. But for now, let's have two parameters. So we say a matrix A is D epsilon spread. That's my main definition here. So we're going to go through it slowly. It satisfies two conditions. First one, which is like the main condition, said any rectangle which is not too small of density 2 to the minus D times the matrix, the average is not much larger than the global average. So notice that this is, first of all, a multiplicative guarantee, not an additive guarantee. And also it's a one-sided guarantee. We only want to make sure that there are no rectangles where the matrix is too dense. We don't care if there are rectangles where the matrix is too sparse. That won't really matter for us. So that's the main condition. The second condition is just some technical condition that you can mostly ignore. It says that for every row, its density is lower bounded by something that's like multiplicative close to the average of A. So for example, if you think about A as an adjacency matrix of a graph, this says the graph is, all nodes have about the same degree, more or less. Again, you can mostly ignore second condition. The first one is the main one. And again, I'm going to fix epsilon from now to just be 1%. So only D is a large parameter. And the whole point of this notion is to say that if you don't have this, if one of these conditions is violated, it should be obvious how we can find a large submatrix that is much denser compared to the original matrix. So let's play this game. So actually, let me just first copy this definition where I just fix epsilon to be 1%. So this is just same definitions. Now let's see. Let's say I give you a matrix A of some density. And I tell you, well, I can find a large rectangle where this is violated. So your matrix on this rectangle is much denser. How can you find a dense submatrix? Well, you go to this rectangle, right? It should be obvious. Okay. Here's the second case. What if I give you that some row is very sparse? How can you find the dense submatrix? Well, let's make it interactive. If I violate the second condition, if there is a sparse row of the matrix, how can I find a dense submatrix?
Remove the row and the filters.
Exactly. Delete the row. Okay. In both cases, it should be obvious what we can do. So we just keep saying if the matrix A doesn't satisfy 1 or 2, we can go to a smaller submatrix that is denser. So we keep doing that until we get stuck. When we get stuck, the matrix has to be spread regular. So it's easy to prove that every matrix A that is not too sparse contains a large submatrix that is this notion of regular. Okay, fine. But why is this useful? This is a very weak guarantee. Such matrices don't have to look random. For example, there could be rectangles where they're completely zero. So at this point, it's unclear why this notion is useful. So I'll tell you why it's useful now. This is going to be the main part. This is this notion of mixing, that individual matrices are not random in any way. But when you multiply two of them, when you mix them together, they become very close to random. And here's like one of the main theorems that we prove. It says, let's read through it sort of slowly. Let's say A and B are Boolean matrices that are not too sparse. Their density is at least 2 to the minus d. And I'm using d for everything here just for simplicity. You can use different parameters if you want. So let's say their density is at least 2 to the minus d. So they're not too sparse. And let's say they're spread regular, where this first parameter is some polynomial in d. Okay, so what can we prove? Take two such matrices and multiply them. It said, and look on their entries and compare the value of A and times B on this entry to what you would expect to get if the matrices were completely random. So for simplicity, when I multiply two matrices, I just mean this average. You multiply A and B, where you sort of transpose B, and you, instead of summing over Z, I average over Z. This is normalization. There's nothing deep going on here. I'm just saying, you multiply the two matrices, and you look at the ratio of that to what you would expect to get if A and B were completely random matrices of, where A had density expectation A and B had density expectation B. And what we proved is that for almost all entries, this value is multiplicatively close to what it should be. So even if A and B are very sparse, we can still get strong multiplicative guarantees to A times B. And if you ever try to apply regularity or any type of pseudo-randomness to very sparse objects, you know that usually sparsity is a serious bottleneck. For sparse objects, you don't really have strong techniques to get strong pseudo-randomness. And the whole point of this is to say this applies also for very sparse objects. Also, if you really want to get very strong tailbound to control almost all the elements of the matrix. Okay, so for example, if you want to think of it as a graph, what does it say? It said that think of this as the graph of A and the graph of B. It says that each one individually is not a very random looking graph, but if I look on paths of length 2 in these graphs, now they're almost uniform. 1 second. מה קרה? אז תרים אותה, תשים את הפח. Sorry, my son just broke a plate. So it says if you take A and B, then the path of length 2, for almost all starting point and ending points, you have about the right number of paths, even multiplicatively, even though these graphs are like very sparse. Here's another way of viewing this, which is the following corollary. So it said the following thing. So here's one way of thinking. Let's say A, B, C are 3 matrices, or you can use them as 3 Boolean functions. And imagine for some reason you want to analyze this type of mixed average. You have A, B, and C, and you evaluate each one of them on 2 out of the 3 variables. Typically, these things are very hard to analyze because there's a lot of correlation between X and Y. There's no pair of random variables here that are independent, right? All pairs are correlated. But really, the corollary, what we put is that if A and B are like spread regular, are notion of regularity, and A, B, C are dense enough, then this type of mixed average is about what you'd expect to get if A, B, C were completely random. So really one way of thinking about this notion of regularity is that it allows us to analyze spread, like sort of mixed averages. that before we didn't have good tools how to analyze, in particular when these matrices were like sparse. Okay, so it's a useful technical tool. Okay. Of course, everything I said up until now is what if the matrices we get happen to be spread regular. But like in the regularity lemma, there's no guarantee of that. Somebody is going to give you some metrics, whether it's in some combinatorial application or in some algorithmic question, no promises. So you also want a regularity lemma that said, take any metrics whatsoever. There is a way of partitioning it into regular parts. And we have something similar here. In a way, it's slightly more complex than before, but still useful for applications. So really here's the theorem. It says, take some matrix A, whatever size you want, any parameter D that you want. There's always a way of partitioning my matrix in the following way. It's a sum of submatrices AI on some row set Xi and some column set Yi with the following guarantees. Well, AI is defined over this rectangle. It's a Boolean matrix. Each AI is either very sparse or spread regular, right? Either very, very random or very sparse. The number of parts units is only quasi-polynomial in the error parameter 2 to the minus d, so it's this parameter. And the rectangles, while they're not a partition, they're close enough to a partition for any practical application. So they don't, on average, they don't cover every point too many times. So by picture, it sort of looks like that. So you find these matrices A1, A2, A3 that are not quite a partition, but they're like, don't overlap much. And each AI is either very sparse or very spread. And really turns out doing this gives you a useful regularity lemma that while it's not really a partition, it's close enough to a partition for basically any practical purpose. Okay. So this basically summarizes sort of the mathematical side of what I want to tell you. Like what is the anonymous of regularity? And what can we say about this? Again, a matrix is regular if it doesn't have a submatrix, it's not too small, where it's much denser, significantly denser. And we can always partition a matrix to a small number of matrices that each one of them is either very spread, very regular, or very sparse. And the main benefit here is that our number of parts is now not exponential in our error parameter epsilon, which we call 2 to the minus d, but quasi-polynomial. So gives us better quantitative bounds.
Shachar, so in the
Yes.
definition of regularity, there was this thing that basically said that each row must have not too small degree.
Yes.
But there wasn't a similar analogous thing for columns. Is that going to become important later on, or?
No, not really.
Okay, so this is enough for.
You could also ask it for columns. It won't make any difference. We don't need it for the application.
Okay.
But you could if you wanted to get it for columns.
Okay.
Yeah, if for some reason it's useful for you. Somehow in the way you do density increments here, you automatically get it for rows and columns. But we only need it for rows.
I see. Okay.
I also wanted to ask, why are you considering AB transpose instead of just AB?
Oh, this is just because if I had A and B, I would need to ask the rows of A to have lower and for the columns of B.
Oh, okay.
Otherwise, I would need this condition too to be rows of A and columns of B.
I see.
So if I want to have rows of A and columns of B, I have rows of A and rows of B transpose.
Okay.
Okay, good questions. Yes. A lot of minor details here. But to me, really, the big picture is to say that we ask for like very mild conditions on A and B. And then on each one individually, we don't get much guarantees, but when we multiply two together, we suddenly get a lot of leverage out of it. So I'll say where this thing is coming from, 1 second. All this line of work. So this is all coming from studying the Kelly-Maker work on 3-term arithmetic progressions and asking, can we understand it in a more combinatorial landscape where there are no arithmetics? So what did they prove? They studied the following question. They asked, what is the densest subset of the integers, 1 up to n, that does not contain a three-term arithmetic progression. It's like a very famous problem, been studied for like a century, many great works in combinatorics, studied it, and along the way invented a lot of very powerful techniques, like for example, the regularity lemma, Szemeredi regularity lemma. And really what happened is that last year, Xander, Kelly, and Regumeka invented a completely new technique and made a huge breakthrough. So before their work, the best bounds, following like a long line of works, said that, well, the densest set of integers without a three-term IP has this size, n over slightly more than a log. And what they proved is quasi-polynomial bounds. And this 12 has since been improved, but that doesn't really matter. So and the reason this is huge is because there is a very famous construction by Baron that says, well, that should be the right answer. Well, maybe 12 is not the right exponent here, but there are pretty dense set of integers without three-term IPs where you lose something quasi-polynomial in the density. And they were the first one to get quasi-polynomial. And it was a huge jump from log to quasi-poly. So that really out of nowhere. Amazing. And the way they did it is by sort of standing notions of spreadness that applies to arithmetic settings, like you have additions. And I'll tell you what they did, and then I'll tell you how we modified the definition to work for matrices, where there is no addition anymore, there's no arithmetic structure. So what did they do? They did the following thing. So instead of talking about integers, it's going to be somewhat easier technically to talk about what's called a finite field model, which is, let's say, F3 to the n. So you have a vector space of dimension n over F3, and ask the same question. What's the densest set here that does not contain arithmetic progressions of length 3? And their key definition was this notion of spreadness that is tailored towards subspaces. They said, well, what is a spread subset of F3 to the n? It's a set that's such that it does not become much denser on a large subspace. Or concretely, take any subspace, an Fn subspace of dimension D. The density of your set on this subspace here is not much larger compared to the global density of your set. Or another way of saying that is that I cannot find a large subspace such that restricting to it significantly increases the density. And significantly means multiplicatively by a constant, let's say 1.01. And what they proved is that if you have two sets that are pretty dense and are spread, and you mix them together by adding them, so you do convolutions. So you add the elements in SNT together, the distribution you get by doing that is very close to uniform. Okay, so this is what they proved. This was, again, out of nowhere, amazing. And really what we did is we found ways of taking their ideas and basically replacing subspaces with rectangles and replacing convolution with matrix product. So the ideas are the same. The proof technically is very different, but the ideas are the same. And actually, since we had this, the people have sort of simplified the proof even further. So now there are even simpler proofs for the things. But conceptually, I won't give you the proof. The proof is sort of technical, so I won't talk about it. But I do want to show you why these notions of spreadness and mixing are useful for some applications. Okay, that's my goal. So maybe before that, are there any questions about all the mathematical stuff that we've been doing so far? Okay. So I mostly want to focus on, so I have here several applications that I have slides on. I think for the, sorry, what?
So is the Bloom is the Kelly Mecca result going to can it be now proven as a corollary of, does it follow from the spread regularity theorem now?
Okay, that's a great question. So the question was, now that we have this sort of this more general version, can we now get the Kelly Mecca version out of it? And the answer is no, we don't know how to do it. And the reason is that because sort of what this combinatorial thing is doing is to some extent stronger. If you could get it as a corollary, you would be able to prove what's called the multicolored version of 3 APs, which, I mean, I can define it, no, then if it's some extension. of the three-term AP problem for which the Kelly-Mecca techniques currently do not apply. Now, if people here have been following this line of work, you know that there is this polynomial method that is a completely different method that applies in a finite field setting. And the polynomial method does extend to these multicolored versions, but it does not extend to integers. Also, it cannot extend to integers because of the integers it will give something that is too good to be true. Now, the Kelly-Mecca techniques, their main benefit is that they are analytic. They're soft techniques. You can adapt them to different settings like integers or other groups. So people have done all the things. But we do not know how to extend them to this multicolored version. And if you could get them as a corollary from this combinatorial setup, then it should more or less automatically give you this multicolored version, which we currently don't know how to do. Okay? So that's like an interesting open problem to explore. So in general, I find, so what I'm telling you is really sort of initial works in this space. Like my intuition is there's tons of potential here, both on the mathematical side, on applications in algorithms, in combinatorics, in other areas that we're just starting to discover here. So if some people here are like this type of analytic techniques in combinatorics and algorithms, I think there's a lot of potential here for new discoveries. Anyways, let me tell you about one application here. Maybe I'll tell you about the first one, this communication complexity one. I think for the sake of time, let's focus on this one. So really, so what are we studying? So what is communication complexity? So I'm assuming many people here know this area, but sort of for completeness, let me spend like a few minutes just describing the area and like what are we trying to discover here. So we have several players try to jointly compute some function, and the input is not given to the players, to all of them, it's sort of split between the players. And the goal of the players is somehow to collaborate and minimize the amount of communication between them. And this is like a very good theoretical model for a lot of problems where you're trying to do something in some shared, between several parts of a system that have some communication channels between them. And really for this specific work, our goal was to understand the power of randomness in this model, in particular when you have more than two players. So in the two-player setting, we understand many, many things. So here's an example. Let's say Alice and Bob want to solve equality. So Alice holds some input x, number 1 up to n, also Bob, y, and they want to see if the numbers are equal. Well, what can they do? Well, Alice can send her input to Bob, and Bob can check if they're equal. But that sort of is a trivial protocol. Alice sends her entire input, she's sending log n bits. And you can ask, can you do better? And turns out that if you use randomness, you can do much better. You can use sort of formally public randomness to simulate a hash function, and basically both Alice and Bob compute this hash function of their inputs, and they just compare the hash values. So only use constant communication. But without randomness, there is nothing non-trivial you can do. Alice has to send the entire input to Bob. Okay, so we've known this for, I know, like 30, 40 years now, and we know many separations for two players, but once you move from two players towards more players, our understanding sort of deteriorates very fast. And what happens when you go to 3 players? Turns out that when you go from 2 players to 3 players, there is already more than one model that makes sense. So maybe the more natural model is something called number in hand. So here we have 3 players, let's say Alice, Bob, and Charlie. Each one of them is holding their own input, and they're trying to do together jointly to solve some problem. So this might be like a very natural model if you come from, let's say, a distributed computing background, where some, agents or some computers or whatever hold some input, they want to jointly do something. But turns out for applications in complexity, this is like a less interesting model. A much more interesting model for complexity applications, and also for some combinatorial applications, I'll tell you about in a minute, is this very unnatural model called number on the forehead. Well, we're here sort of, the input is sort of split between the players, but each player gets to see more parts of the input. Like in this case, Alice would see Y and Z, but not X. Bob would see X and Z, but not Y. And Charlie would see X and Y, but not Z. And by the way, the reason this model is called number on the forehead is because here's another way of thinking about it, is at the card game. Alice had the X stuck on her forehead, Bob has Y, and Charlie has Z, and each one of them can see the input on the forehead of the other players, but not their own forehead. So Alice, for example, could see Y, which is on Bob's head, and Z, which is on Charlie's head, but not X, which is on her own head. Anyway, this is the reason why people invented this name. But for us, let's just think about it as 3 players, 3 inputs. Every player gets to see 2 out of the 3 inputs. So of course, now the players have more information. It should be easier for them to solve problems. And the question is, by how much? Does it make every problem trivial, or can we still prove some lower bounds on some interesting functions here? Okay. So this is the model I'll be talking about from now on. Okay. Again, our goal would be to prove lower bounds. And here's a serious bottleneck. We don't have good lower bound techniques here. We have basically only one lower bound technique in this model. And this lower bound technique is so powerful that it applies both for deterministic and for randomized protocols. And as I'll tell you in a second, there are interesting problems in this model that are very easy for randomized protocols, but for which we don't know how to prove strong lower bounds for deterministic protocols, although we believe that there should be. And also we know that these lower bounds for deterministic protocols have a lot of deep mathematical content. In particular, they have equivalent versions that are famous problems in additive combinatorics. So I'll tell you about 2 examples. Here's the first example. This is called the exactly n function. Imagine now the inputs are like numbers 1 up to n, and the players want to see if they sum to n. Seems like a very innocent goal. How hard can this be? Well, if you use randomness, you can use the same hashing tricks to solve it with constant communication. It's still easy. But if you don't have randomness, we don't know how much communication this requires. For such a basic function, we don't know the answer, even asymptotically. And there's like triple exponential gaps between lower bounds and upper bounds. It's amazing. Really don't understand. But we do know that this problem is equivalent to something known as the corners problem, which is like a very famous open problem in additive combinatorics that I'm not going to define here, but just if people want, I can define it later. But again, this innocent problem in number of default communication, completely equivalent to a very famous open problem in combinatorics. Here's another example. This is called the partitioned function. Now the inputs are subsets of 1 up to n. And the players just want to see if they form partition of 1 up to n or not. Again, within randomness, it's easy. Without randomness, we don't know, but we know it's equivalent to another, even more famous open problem in combinatorics called the Hess-Jewett problem. Here the gaps are even larger. Although recently have been like major progress on Hess-Jewett for like 3 players, but still huge gaps between upper and lower bounds. So there are these very basic, easy to define problems. Then when we have this sort of shared inputs between players, we're at a loss. We don't have any good lower bound tools how to prove that things are hard without randomness. And this was our goal. Our goal was to say, can we find maybe these ones or some other functions for which we can actually get strong deterministic lower bounds?
Would these problems become the same if you treat a set as just a n-bit number with 1, 0, 1s?
Sorry, I didn't hear you.
Would these 2 problems, the sum check and this partition problem, would they become the same if you treat the set as an n-bit number with 1s in the elements that are in the set and 0?
It's the same, it's just whether how you define n to be n or 2 to the n. Yeah, if you wanted to be the same scale, maybe here you would say 2 to the n instead of n.
I see.
Like this is log n bits, this is n bits, but again, for both of them, yeah, I agree, they don't live on the same scale, but it doesn't really matter. What I want to demonstrate is that, for both of them, we are super far from any reasonable lower bound. Like all the lower bounds we have are like, triple exponential or worse compared to what we believe the answer should be. Okay. So we saw these 2 examples of functions that are easy for randomized protocols, but sort of we believe they should be hard for deterministic protocols, but we don't have tools how to prove that. But if you do some counting arguments, then it's not that hard to show that such functions should exist. There should be functions that are easy for randomized but hard for deterministic protocols, again, just by sort of doing some counting arguments. And our main goal was to say, can we find some function for which we can prove this? And the best that was known before our work was based on these sort of corners, which you see these sort of double exponentially worse than what you would want to get. Okay. So here's what we proved. Again. Okay, sorry. So here's what we proved. There is an explicit function such that it's easy for randomized, but it's hard for deterministic protocols. So ideally, we would like to get log n. That would be the ideal goal here. But we get log n to some constant, like in this case, 1/3. And remember, before, all the previous techniques will prove log n. So this is already major progress for us. We got polynomially close to the right answer. And this function is not some crazy looking function. It's actually a very simple function. Here's a function. So it's basically the following thing. To identify your input space as some vector space, fq to the k, where the dimension is some just large enough constant, like 40, that's enough. And q is some big parameter. So it's a large field and constant dimension such over this field. And I'm thinking of the inputs as vectors in fq to the k. And the function is 1 if all the three inner products are the same. Okay, so anyway, it's some relatively simple function. And when you view the theorem, you'd say, well, this function looks very algebraic. Maybe the proof is also very algebraic. And the answer is no, the proof is not algebraic at all. It's just using this spread regularity. And all that we're using about this inner product is sort of like a good two-source extractor. So this has some nice pseudo-random properties. Okay, so we're not really using anything algebraic here. This would have worked for many other constructions as well. So what I want to tell you is how proving lower bounds for this is even related to all the first half hour where I told you about spread regularity. I want to show you the connection. So how do we study protocols? How do we study deterministic protocols? Well, we study them by studying their combinatorial structure. So for example, if I have a two-party function of two players, protocols correspond to partition of the matrix into rectangles. Okay, simple looking shapes. And if I have three players in this number in hand protocols, turns out that here protocols correspond to partition to cubes. And for this more complicated model of a number on the forehead, you get partitions into more complicated structures called cylinder intersections. What are these cylinder intersections? Turns out that studying cylinder intersections is essentially the combinatorial core of proving lower bounds for this NOF protocol. So we just focus on those. So a cylinder intersection is any function on three inputs, x, y, z, that can be factored like that. It's some condition on x and z, some condition on y and z, and some condition on x and y. So why is it called cylinder intersection? Because of the following picture. What is AXZ? It says x and z should satisfy some arbitrary condition, should be in some set A, but this completely ignores y. So if you think about this shape AXZ as a three-dimensional shape, it's basically a cylinder, right? It has some arbitrary shape in the XZ plane, and then you just put it all across the y. And you do the same thing for XY and YZ, and you intersect them. So you get these weird looking shapes, but really geometrically they look weird, but really from a functional perspective, they're just functions that can be factored like that. Maybe here looking at things functionally is more intuitive than looking at them geometrically. And we want to study such objects. So again, I'm not sure the connection, but trust me that studying such objects is really the main mathematical challenge in proving lower bounds for these NOF protocols. So let's say f is our hard function. We're trying to prove that there is no efficient protocol, deterministic protocol that can solve it. So let's say towards a contradiction, it had an efficient protocol. Turns out that what this would show is that there is a large cylinder intersection that is completely supported on the ones of f. Okay? So this is something you can get sort of just by studying these protocols. So this shows why it's interesting to study such serial intersections. Now let's assume just of a pipe dream that when we do that, somehow magically this A is spread regular and this B is spread regular and all of them are dense. Well, if this happened, then our mixing theorem would imply that this CI is dense. So this talks about the projection to the faces. If they're all dense and these two are spread, then our mixing would say, well, there should be many solutions here. But if the function f, we choose it to be sparse enough, this will give us a contradiction. So again, I know this is very much hand-wavy, but I just want to show why studying this spread regularity is a good tool for us. And really getting the good quantitative bounds for spread regularity is what allowed us to get these polynomial bounds here instead of this sort of exponentially worse parameters that people need to get before. And again, if you don't do that, then anyways, there's some, I think trying to explain the details here is going to be too much for a limited time, but I just want to get the high level picture that the spread regularity is what really allows you to control these shapes, and these shapes is what control these NOF protocols. Anyways, very, very much hand-wavy. Now I'm wondering, how much time do I have, and should I go into a few more applications or not? Or maybe I should just summarize. So how much time do I have left?
5 minutes.
Okay, so maybe I'll just skip the other applications. So there are other applications, but we're going to skip them. And this is combinatorics. I'm going to skip those also. Let me just summarize. So we have this new notion of regularity. Main benefit, better parameters, better control in the number of parts in terms of the number of error. Main drawback, sorry, whatever notion of pseudo-randomness we get here is much weaker. But we get mixing. You multiply two, so this weak notion of pseudo-randomness for matrices, spread regularity, they become very close to uniform. And this turns out to be very useful for applications. And I told you about one of them. And really, if people here are interested in the details, you can email me or talk to me, but really this talk is based on 4 papers. So this first one is the one where we develop the techniques, the combinatorial techniques for the application in number on the 4, for the communication complexity application. The second paper is where we develop the regularity lemma and some algorithmic applications. And these 2 last ones are for more combinatorial applications, about problems related to corners. Actually, here we found some bug in the paper, but now it's sort of, we know how to fix it more or less. So at some point, we're going to have like a fixed version on that. Anyways, if people care about the details, if not, ignore it. So what about next steps? Like I told you, I really feel that all these works are just a starting point. We have this new tool. And for me, what's exciting is there seems to be so many different directions you can try to develop this tool. And depending on whatever you're interested in, depending on the applications. And I just want to show you a few things that I think are potentially possible and I think are very exciting to explore. So one is in combinatorics. Like, I really think that this is, now we have the right tool to maybe get much stronger quantitative bounds for problems that before we didn't really have good tools. So one of these problems I told you about is called the corners problem that we're exploring now. But here's something that to me is very tantalizing. There's this famous lemma called the triangle removal lemma that probably many people have heard about, where the only proof we have is basically based on either the Szemeredi regularity lemma or some improvement by Jacob Fox, but still you get a power type bounds. But we don't have any power type lower bounds. The lower bounds here are quasi-polynomial. So one thing we've been trying to work on for a while now is to ask, well, maybe you can get better bounds for this triangle removal lemma. For now, we don't know, but I have hopes that maybe we can do something. We will see. So again, and there are many other combinatorial applications where, people have used the regularity lemma, but maybe now you can use this weaker notion and get better quantitative bounds. That's one aspect. The other aspect is algorithmic. So here the application I didn't tell you about is that we can design an algorithm for matrix multiplication that is completely combinatorial, meaning doesn't use any linear algebra. It doesn't work as well as stress-n, but it works better than the trivial, naive n-cubed algorithm. And one thing that we've been trying to explore here is both whether we can get better speed-ups for other problems, but more interesting is the second goal. So, stress-n and all these linear algebra techniques for multiplying matrices only work for matrices. They don't work for tensors. So, for example, if I tell you you have like a 3 uniform hypergraph, and you want to see if it contains a 4-click, we have no non-trivial algorithm. Like all the algorithms run in essentially trivial time. Because the only trick that we know, which is using linear algebra, we don't know how to apply it here. So we're stuck. So another direction we're trying to explore here is how can we maybe expand some of these techniques from matrices to tensors. And if you ever work with tensors, you know that many things become much more complicated once you extend them from matrices to tensors. So there's no exception here. So we know a few things, but a lot of the things are still a mystery.
Shachar, so those are for Boolean matrices or for arbitrary matrices?
So these ones are for Boolean matrices. You can also ask about arbitrary matrices. You can ask about what if I don't have standard product, but we have min plus, or we have, min max. So all of these are good open questions that we're exploring now, and I don't know, may or may not lead into something. We'll see. But yeah, I think this is what I said. There's so many different directions here. If you want to do fine-grained algorithms or fine-grained complexity, or you want to do combinatorics, or you have this new tool, you have this new hammer, and now you have to find new nails or to develop this hammer further, right? And really, for me, again, I'm more interested in the analytic side than the algorithmic side. So really, this question of moving from matrices to tensors to me is very tantalizing, because matrices really talks about analyzing these types of averages. Now we know how to do this type of like mixed averages. And analyzing those is basically this core of this work on 3-term AP and matrices and everything. But the current techniques don't extend beyond that. They don't extend to 4-term progressions. They don't extend to tensors. And really turn out that what you want to be able to analyze, if you want to extend everything we know from 3 to 4, meaning 3-term APs to 4-term APs, 3 plus to 4 plus, graphs to hypergraphs, everything is really all about finding tools that allow us to analyze these types of averages, where we have 4 variables, and every function is of 3 out of the 4. So you think, well, what's the difference? This is 2, this is 3. Well, once you study the details, huge differences, many things break down, and we're slowly trying to develop the theory further. But I feel that if we are able to analyze these things, if we're able to define notions of spreadness that applies to tensors and prove mixing for tensors, my guess is this is going to have many applications. We'll get faster algorithms for problems that for now we have no non-trivial algorithms. We'll get better bounds for problems in combinatorics. We have no bounds, and so on. So I feel like this is the main analytic question here. Finding the right notion of pseudo-randomness and finding the right notions of trying to prove mixing on these more complicated notions. And I think that's a good point to stop. So thank you.
I have a question.
Yes.
So this the log n to the 1/3 in the lower bound on the NOF thing, is this related? The 1/3 is this related to the 1/12 in Kelly makeup? Is there a common?
Yes and no. I mean, they get the 1/12 because they try to do more things. Somehow in the combinatorial setting, we can get better parameters because we're trying to find less rectangles and not like subspaces. Also, we know that our techniques will never give us more than 1/2, better than 1/2. And this 1/2 is sort of related to this barren construction that shows for some of these problems, you cannot beat 1/2. So not necessarily for this NOF problem, but for other problems, we know that 1/2, like for example, for this sum check problem, checking if x plus y plus z equals n, we know that there is a square root log n algorithm, communication protocol, based on barren construction. And while we don't know it for our function, these techniques don't really differentiate with different functions. So for this type of techniques, the square root log, this exponent of a half is a barrier, but we cannot get a half. For some reasons, we get a third.
And these techniques don't go from number on forehead to 3 players to 4 players for a similar reason.
Yes, so I said, if you want to go to 4 players, you need to be able to analyze these objects that currently we don't know how to analyze them. You need to basically say, I need some extension of some pseudo-random property of tensors that if it holds, then this average behaves like they were random and unrelated to each other. And there are natural ways that you could try to extend this notion. But currently the proof techniques fail for like a variety of reasons. But I still think this is like the most promising direction forward. Just turns out to be complicated.
Let's thank Shachar.
Thank you.
Bye, Shah.
Okay, it's good seeing you all. By the way, Arkadev and Yogesh, are we meeting this week or not? What was the plan?
Yeah, let's meet tomorrow.
Tomorrow? Sure. So what time?
What time tomorrow? Well, more or less when the meeting, when we started the talk today. So
Tomorrow evening.
tomorrow evening.